Good morning, everyone. Thank you for waking up early. John Max in So my name is Nick Holliman at King's College in London, and you may know me better from the SDNA conference if you've been here before, because I'm normally in stereo sprays doing these. I guess very often like this talk, trying to bring some psychophysics and psychology into the world of electronic imaging. So my co-authors here are Arzu Hodgkin at Technology in Switzerland, Sarah, Lucy and Michael at Newcastle University in the UK, and Andrew Woods, our spotted here, who's also eloped from the conference, to help present this paper. And we'll talk today about entropy ordered shapes as bivariate glyphs. This is something where we started quite a long time ago now. It's been delayed by COVID and by illness of one of our co-authors, but last week I'll present something about it. I'll give you a little application context, talk about some theory and empirical results, and then some more applications at the end. One of the things we've been working on for quite some time now is digital twins and how to visualize information about them. And we were using these very simple glyphs, little discs with colour showing temperature across the 3D model of the city. This is Newcastle upon Tyne. And we were showing these to the City Council, and they were saying, well, we know some of these sensors are not reliable, they cost very much, so they can't be that reliable. Can you show us something about the quality of the sensors and the search of the values, which set us off on a track which led us to these bivariate glyphs, which may or may not be used in sensor visualization.
Move your microphone to here.
Maybe a sound issue. Just been fixing the sound. Not quite English voice. My real Australian accent. How's that? Is that any clearer? Good. Okay. So for I just said very much about what bivariate data is, but it's some data with two values you want to visualize. In this case, it was mean temperature value of an hour, and it's variable source standard deviation. And typically from the sensors, you get these falling or rising lines of temperature through the day with measurements wiggling about around this. But that's almost by the by. I'm going to step briefly into information theory and then quickly out again in order not to upset anyone in the room. I very much like information theory as a model of information transfer from a source to a destination, but destination might be human. I spent many years thinking it was bonkers to look at it like this, because humans are not information theoretic receivers in the Shannon sense. We make stuff up all the time. Shannon receivers back there. But it gave us an idea that we might want to use entropy, or information itself, as a visual cue. And you'll see that quickly translates into something very easy to understand. But that's where that came from. I also like the fact that this highlights information transfers through the pipeline from digital to optical to neural. And in many, many visualization papers, people don't really relate, particularly to the middle bit. They don't consider displays as part of the visualization pipeline. They assume they're all the same. Anyway. So what we were really looking at in the end turned out was shape complexity and visual complexity. You can look at that in a number of ways, going from high to entropy. And if you look in the psychophysics literature, there's a history going back at least the 1980s of understanding this. This is some work by Ketty and Garvin on the right. These are fractal shapes, and they showed that people could order the fractal shapes by fractal dimension. So there was some innate ability to order shape by some measurable thing. And then there's also the work at the University of Western Australia by David Parcott's group, he's retired, which showed that you're very sensitive to very small deformations of shape. So if you can find some ways of using shape, you're very sensitive to this. In contrast, in the visualization literature, there's been a long history of ignoring shape as a possible visual cue. Going back to Bertin, 1967, who argued, without, as far as I know, any empirical evidence, that shape couldn't be an ordered quantity and couldn't represent quantities at all. In fact, he was quite dismissive of shape as a thing. He understood there were different shapes and you could use them for different things, but as an orderable cue, he didn't use that. Just looking at a couple of others, McKechnie in 2012 did a study which I think by today's standards would be quite questionable, but agreed with Bertange in that study that shape was really a useful visual cue. And many others, in Manson's textbook, 2014, and many others presenting, have really taken Bertange's work and just assumed it was the truth. Perhaps one of the most recent papers I know of who started questioning that was Chan and Daniel Archambault, who's now at Newcastle, in my old job. And they ran a set of experiments with groups of shapes, showing that shape, people would judge shape sets to be ordered or not. They didn't have a predictor to show how shape could be used, but it did begin to show that shape was possibly orderable. If you're a static physicist, this will seem possibly obvious. If you're a visualization person, you get very frustrated with all textbooks. So we came up with this modification to our original glyphs, where we're going to use shape around the outside of them to represent the second quantity. I'll show you some different examples of that at the end. And we had a calculation, sample entropy, which is used in medical data analysis, for predicting the order of these shapes. And that sample entropy value predicted this order for those shapes, which you could also not unreasonably predict from the frequency value of the generating signal from them. We put these on a log scale to make differences quite big. We didn't want entirely indistinguishable shapes. And then we ran a pairwise experiment on testing if people could indeed order shapes with a null hypothesis that you couldn't do it, which we agreed with Bertan. We ran a pilot in the UK, and we ran a set of replication, sort of self-replication trials across the world, which is also in Switzerland and Andrew in Perth. I don't know which country you're in for a second. Helped us run in person before COVID, and then we have switched to an online set of studies during COVID. And we got back in total around 87 participants. First time through, we ran a whole set of statistics on this, which showed it worked really well, but the wrong statistics. So we spent another 6 months redoing statistics with some help from a local professor of statistics in Warwick. And so in the end, we used these exact binomial tests. And what this is showing is the scores for people who are asked to order the shapes, who got the order correct in each pair for that shape. And you'll see that the scores are well above the chance line. Chance line is 50%. Even in the worst case here, the correct answers were running over 80% of the time. So it seems that people are pretty good at ordering shapes with a large effect size, certainly well above chance most of the time. So we've got a hypothesis, we can predict what all the shapes are in, and we've shown that they probably will work. We also wanted to do a quick test at the time on whether you could search for these shapes within the original pictures of the city. So we put them back in the city and use value rather than anything specific. We could search for and ask them to look for a low and a high value. And they could do this with a single detection test with high discriminability of bias. And the only thing that really came out of that, there was a difference in response time between the simpler glyphs and more complex ones. And we tend to see that, but these are close to the limit of visible on the displays we're testing on, so that's probably not so surprising. Okay, so we've used those tests. Does that mean I don't stop? Okay. And produced a software library called Vizent. Vizent is the European bison, anyone who's worried about what it is. And the first two rows in this we've predicted with some shape complexity metric, with sample entropy metric, and tested them empirically. The other three we haven't tested as yet. And you can download it and try it out in 2D visualizations to a house content. You don't want to code them yourself. This is the original urban digital twin software with the glyphs showing, in this case, median temperature and standard deviation over an hour of that temperature. It might be a bit small from where you are, it's designed for a bigger screen closer, but you can fairly easily pick out those with high standard deviation, that might be the worrisome ones, and vice versa, those that are more reliable, which is our original aim. We've not tested that yet, that's one of our next things to do. This was a similar visualization, but slightly different. This was the European heat wave last year. We had, these are the major cities, over 1 million inhabitants in Europe. The colours show the mean temperature for one day, and the shape is showing the difference from the 20-year mean. And that has a negative and a positive thing, so we're using different shapes here for negative and positive values, and the square wave generators for the negative values. And hopefully you'll see that these work reasonably well. You should be able to spot the triple E at the bottom, probably can't read the text from where you are. 10 degrees over its 20-year mean, at 42.5 degrees last time, which isn't as hot as Australia, but it's surely hot for Mediterranean. We've also tried them out in this, you'll probably know in this handwriting recognizer convolutional neural network as a visualization, quick visualization of the probability of the results. So on the left is a 2 withdrawn, it's classified as a 2. I say probability because machine learning doesn't know what probability is, but what it reports as probability, it thinks that 2 is very strongly a 2. It thinks the 9 might possibly be a 4, and it thinks the 3 might be a 5, but it's really very uncertain about it. And that kind of quick, at a glance, understanding of the second variable is what we're really after. Okay, I'll show you a short film, I hope. I've got a missing talk, so it's probably time. It's just 2 minutes. The glyphs here are used to do different things. The colour is used for time, and the shape is used for a count. And you'll see what it's about when I say go. The protest he's talking about was a Just Stop Oil protest in the centre of London last November.
In November 2023, a protest closed Waterloo Bridge to traffic. This interrupted the two-way flow of buses on the bridge. How did this affect the surrounding road network? At CUSP London, we used real-time bus tracking data to investigate. Here, you can see the normal morning bus traffic on Waterloo Bridge and nearby streets. Even now, you can see a small number of congested areas. At just after 9 a.m., the protest started to close the bridge northbound. The result was congestion at the south of the bridge and near Waterloo Station. As both directions become blocked, congestion ripples out north and south of the river. From 10:12, the protest northbound is clearing, and congestion levels begin to reduce. By 10:38, the protest southbound is also cleared, and full recovery is underway. Eventually, normal traffic is resumed, and the disruption is over.
Okay, so I'm going to talk. So the takeaway is that, unlike Bertrand's original book, and people have repeated that since, we think there's evidence that sets of shapes can be perceptually ordered. In the visualization world, I don't think if you're a psychophysicist that's going to be a surprise to you. And that perceived order could be predicted with some kind of visual complexity calculation, visual entropy calculation. We're doing that at the moment with sample entropy, but we're in the process of testing 16 different metrics to see which ones work best. And I can say some of the ones in the literature work really, really badly. And some of them are very good. And we think there's somewhat of a beginning of evidence that these shapes can support bivariate glyphs, which we hope are easy to use, and can present things like mean and uncertainty for quick access to that data before you dive into the details. And although we've shown digital twins, the type of people we're talking to is about this, the defence simulation analysts who want to convey to government very quickly results of, with mean and uncertainty. They're struggling to get uncertainty across to government. And other people trying to convey mathematical modelling results to the public. You won't be able to see it because it's pretty small, but the one on the left is a COVID representation from September 2022, showing COVID in London. And the glyph shape simply showing whether things are going up or down in the zone. There's no particular value associated with it. Okay, I have to thank David Firth of Warwick University for his help with statistics. This work was funded partly by the Alan Turing Supercom project from SRC, partly by Cusp London ourselves through our current research software engineer. And thanks to my co-authors for all their work over the years. Thank you.